We know that the speed of light in all directions, regardless of motion of the source or receiver, is always constant and absolute. The reason is Michelson Morley experiment. In 1887, Albert Michelson and Edward Morley conducted an experiment that sounds a cornerstone in history of physics. The idea was suspending a platform on Mercury, and they used an interferometer to check the speed of light in all directions, and they showed that it is the same. You may wonder, is it that necessary to do that? Yes. Newton believed in ether. He believed that something called ether permeates the space. Let's say we have a glass container including some air particles. If you evacuate the air, Newton believed that you cannot evacuate the ether. That's why the light can pass through the vacuum. You may say, okay, let's believe in ether. What happens next? Michelson and Morley said, okay, if we have some ether in space, as our solar system, our galaxy is moving in ether, is moving in space, so ether must be in a steady state, at rest, and when we are moving in ether, it sounds like a relative motion. Relative to our solar system, ether is moving because we are moving in a space and ether permeates the space and it sounds at rest. Okay? And if we shoot a beam of light against the ether, and as the light must travel through the ether, basically the speed of light is opposed by the motion of ether. And if you do the same thing in perpendicular direction, perpendicular to the direction of the ether flow, you might have no opposition. So the speed of light must be larger. But they found that both are c, so they rejected the ether. From that time, Einstein got inspired to think about relativity. You know that one of the very important principles of relativity is that speed of light is absolute and not relative. How do we know that? It's just because of the Michelson Morley experiment. So they changed the physics forever. Let's do a hypothetical experiment. There is a bulb on top of this train. You are at rest on the train, and also train is at rest on the ground. It flashes for a moment. A spherical light, spread out in a space in all directions symmetrically. If the speed of light is taken to be 3 times 10 to 8 meters per second, we expect after 1 second the radius of this sphere in all directions to be 3 times 10 to 8 meters. So far it's easy. Now let's do the same experiment when the train is traveling rightward. When it flashes, as the speed of light is considered absolute, although you are moving, you cannot catch the light. So the speed of light is still in forward or backward direction is the same for you. It sounds very strange, but still we have the same result. In all directions, the speed of light after 1 second implies that the radius of this sphere to be 3 times 10 to 8 meters. Now let's do something very strange. Uncle Albert is waiting for you on the station. You are passing by, and immediately when you pass by, you flash the light on your train. You are moving, he is not. Okay? At the moment when you flash the light, Uncle Albert believes that a flash of light starts spreading out in the space in all directions, so the radius of the sphere of light should be 3 times 10 to 8 meters after 1 second. Same for you. You have also your own spherical wavefront. You are at the center, and you have the same radius. It sounds very strange. How many spheres do we have? 2. How many centers? 2. Everybody believes that they are at the center of their own sphere. But can we observe both of them? No, you can't. You can be at rest and talking with Uncle Albert, and you can see this sphere. And if you are traveling with the train, okay, you may see the other one. You cannot observe both. And it's very strange. We do have 2 different spheres, both exist, but we cannot see the other one. Everybody has their own spherical wavefront. I know this is very strange, but this is very important. Welcome to Relativity. Okay, thank you for watching this video. Let's proceed to see what's going on next.